Hello everyone, welcome to Physics 205. So in this video, I want to go over the solutions for the in-class practice for the dynamics or Newton's second law problems. Okay, so in this first problem here, this first question says an applied force of 120 newtons, so applied to the right here on this box, and a kinetic frictional force of 50 newtons act on a box as shown below. What is the mass of the box if the acceleration is 6.0 meters per second squared? Okay, first of all, there are other forces acting on this, right? We didn't draw all the forces here, and let me just show you the other forces. The box also has a weight, right? The gravitational force acting on the box, the force that the Earth exerts on the box, so that's acting down, weight. These are all vectors as well. And then there's a normal force at the surface, so the floor, whatever it is, exerts on the box, that's upward, and that's N, right? That's a normal force. Now, because we're given information about the acceleration and it's pointing right in the x direction, this acceleration here is really ax, right? So really we know ax is 6.0 meters per second squared. Okay, so we really don't need the y information, but let me just walk you through this and go through the y information as well, just so you get some practice on how to do this. I'm going to apply Newton's second law to the y direction. Now, first of all, I need a coordinate system, right? Because I know the box is moving to the right, I'm going to say that that is the x direction, and then y will be vertically upward, right? So that's my coordinate system. So if you think about this, if I want to look at the sum of the forces acting in the y direction, that's got to equal the mass of the box times the acceleration in the y direction. Well, if I want the sum of the forces acting in the y direction, that means I want the y components of all the forces. So if I'm doing this carefully, I'm going to write, I want the y component of the normal force, plus the y component of that applied force, plus the y component of the weight, plus the y component of the kinetic frictional force, and that's equal to MAY. Okay, so we have to ask ourselves, if we look at each force vector here, how much of it is in the y direction? Well, if I look at the normal force, since it's pointing straight up, all of it is in the y direction, right? I don't even need to do any trigonometry or any sines and cosines in this case, because it's acting directly along the positive y-axis. So all of n is in the y direction and it's positive. So ny, the y component of n, is just all of n, that entire magnitude. What about the applied force? How much of that force is in the y direction? Well, none of it, right? So that's going to be 0. It's all in the positive x, right? None of it is in the y. The weight, all of it is in the y direction, and it's negative, right? It's acting downward. So I can write that, remember, weight is just mg, so I can write that as minus mg. And then how much of the frictional force is in the y direction? It's all in the negative x direction. None of it is in the y, so that's 0. And we have a constraint here. This box is not moving in the y direction at all. So its acceleration in the y direction is 0. So m times 0 is just going to give me 0. So if I move that mg to the other side, this just tells me in this case that the normal force is equal to the weight of the box. Okay, that'll be important later. When we don't know the actual frictional force, we have to find it by using the coefficient of friction. But for now, it's true, but it's not going to be useful in this particular problem, right? But I wanted to kind of work it out. Now let's go to the x direction. Here's where we're going to solve the question. So I also have that the sum of the forces in the x direction equals max. So now I want the x components of all these forces. So nx plus fx plus wx plus fkx, and that's got to equal max. Well, now what is the x component of normal force? Well, all of it is in the positive y direction, right? So none of it is in the x. What about F? The entire force F is in the positive x direction. So it's plus F, right? That entire 120 newtons. The weight, well, the weight is in the negative y. There's none of that vector is in the x direction. So that's 0. And then the frictional force, all of it is in the negative x direction. So I'll just write minus Fk. And and that's got to equal MAX. Okay, so we could solve this for AX right now if I divide both sides by, so right now I have this. I'll write it on the left-hand side. MAX equals F minus FK. So I'm going to divide both sides by M. M's cancel, and I get AX. Actually, no, I got to be careful here. I want to solve for M, right? So let me go back. So I have MAX equals F minus FK, right? I already know AX, so I want to solve for M. So I need to divide by AX. So I leave M. Okay, so now I have M by itself. That's F minus FK over AX. And we have all those values, right? Remember, the applied force is 120 newtons. The frictional force was 50. And the acceleration was 6. And if you work that out, you're going to find that this is 11 point, I'll do 3 sig figs, let's say 11.7 kilograms. So that's my mass, right? That's the mass of that box. Okay, and again, we found it by applying Newton's second law in the x direction. Okay, second question. You're told a 65 kilogram woman in an elevator is accelerating upward at a rate of 2.1 meters per second squared. What is the net force acting on the woman? What is the weight of the woman? What is the normal force acting on the woman? If the woman were standing on a scale at this instant, what would the value of the scale read? Okay, so I'm going to draw a picture. Let's say this is the elevator. So here's the woman standing on the floor of the elevator, or you can even think of it as a scale. Later, we want to have a scale there. And what are the forces acting on the woman here? Well, at our center of mass, we have the weight, right? Her weight is acting down, that's mg. There's a normal force that the scale or the floor pushes up on her, that's n. And we know that this elevator is accelerating upward. This is not a force, but I'm just drawing it in to show that the acceleration is going to be in the upward direction, and that's equal to 2.1 meters per second squared. Okay, but again, that's not, the acceleration is not a force. The only forces acting on her in the vertical direction are the normal force and her weight. Okay, so the first question is, what is the net force acting on the woman? Well, remember, in general, right, if we look at the sum of the forces in the x direction, which is called the net force in the, sum of the forces in the y direction, which is called the net force in the y direction, that's got to equal MAY. So if I want to find the net force, this is part A here, then the net force is simply going to equal the mass times the acceleration in the y direction. So her mass is 65, and then the acceleration was 2.1. So if you work that out, it's going to be 136.5 newtons. So that's the net force. It's really in the y direction, but that's the only force, right, acting on her. When you combine the normal force and the weight, you get this net force in the y direction. So if you want, you could say that the net force equals that magnitude, and it's at 90 degrees, right? Because it's pointing upward. Okay, another way to think about it, if we look at the vectors here, right? This is the normal force. This is the weight. If I add the weight, I'll put the tail of the weight at the tip of the normal force. And then my resultant vector is going to be from the tail of the first, tail of the normal, to the tip of the second one. That's my net force acting upward. And I know it's acting upward because the entire thing, she's accelerating upward, right? So it has to be acting in the upward direction. Okay, what is the weight of the woman? All right, so to figure out the weight of the woman, that's easy. That's just mg. Right, so the weight, the magnitude of the weight is mg. So that's going to just be 65 times 9.8. And if you work that out, it's 637 newtons. Okay. And it's acting downward, right? If we want the direction, it's acting downward. So at 270 degrees, or you could say, 90 degrees, or you could say south, right? It's acting south. All right, what is the normal force acting on the woman? So now we need to split this up, right? So again, I'm going to use the sum of the forces in the y equals MAY. But now I want the y component of the normal force plus the y component of the weight. That's got to equal MAY. In this case, the y component of the normal force is the entire normal force, right? It's all acting, and we don't know what the value is. The y component of the weight, it's all acting in the negative y direction, so it's negative the entire amount of the weight, and that's got to equal MAY. So actually, if I solve this for normal force, I can add W to both sides. So normal force is equal to the weight plus MAY. Okay, and we know all those values, right? Or you could even write this as mg plus MAY, right? Because we know the weight is mg, but we already calculated the weight, so I'm just going to use the value. So this is going to be 637 plus, and then it was 60, her mass was 65, and the acceleration was 2.1. So in this case, I'm going to get 773.5 newtons. So that's the normal force acting up on the woman when she's in the elevator, accelerating upward. And notice that this value is greater than her weight, right? And we kind of knew that when I drew the picture here, right? So this value right here, which is 773, is greater than the weight, which is down at 637. So we have this net force up of 136.5. Now, the last question was, if the woman were standing on a scale at this instant, what would her value in the scale read? Well, the scale reading is going to be the normal force, right? Because the scale is reporting the force that the scale exerts on the woman. So the scale reading is just going to be the normal force. So I'll write that here. Scale reading is equal to the normal force. So that's going to be 773.5. So she's going to appear to weigh more when she's accelerating upward. If she were moving at a constant velocity on the elevator upward, then her normal force and the scale reading would be exactly equal to her weight, right? Because it'd be no acceleration. So just be equal to W. N would equal W. If AY was 0 here, right, this would just be normal force equal to the weight. And then if she was accelerating downward, this would be negative, and her normal force would be less than her weight. So a scale reading would be less than her normal weight when she's just standing without accelerating. Okay, great. Next question. So in this question, it says 2 boxes of mass 20, M equals 20 kilograms. So they each 20 kilograms are connected by a rope, and the first box is pulled with a force of 500 newtons as shown below. Assuming the boxes are on a frictionless surface, what is the acceleration? All right, so there's no friction, that's good. What is the acceleration of the system of the 2 boxes? And what is the tension in the rope between the 2 boxes? Okay, so we're looking for, this whole thing is going to be accelerating the whole system. So we want to find that. And we want to figure out what that T is, what that tension is. Okay, now, again, there are forces acting in the y direction as well, but we don't really care about it in this case because we're only interested in what's happening in the x direction. Remember, my coordinate system, I'm going to assume x is to the right and y is vertically upward. There's a couple ways you could do this. You could assume that these 2 boxes here, right, are one system. and this force is applied to just that entire system and get the acceleration immediately. Or you could break this up and look at each individual box separately. Let's actually break it up because I think it's more instructive to walk through this, and we'll get the same answer. So I'm going to start with, I'll call this box 1, and then this is box 2. This is 1 here, and this is 2. Let me start with box 1. All right, what are the forces acting on box 1? Well, again, we have the weight, we have the normal force, but we don't really care about those for this part. There's no friction, so nothing to the left, and then, but I do have this tension acting to the right here. Okay, and then on box 2, I have the weight, so W2, the normal force. I have a tension, but now remember that tension, that rope is pulling to the left. And then I have this applied force to the right of F. Okay, so let me apply Newton's second law to that first box, to box 1. So I have sum of the forces in the x direction is equal to m1ax. But it's the same mass, I'll just call m-ax. Okay, so I want the x component of the normal force plus the x component of the tension plus the x component of the weight. That's got to equal max. Well, the normal force and the weight are acting in the y direction, right? So there's no components in the x for those two. But the tension is acting in the x. In fact, all of it is. So that's the entire tension T. And that's got to equal max, which I'm just going to call A because we know that these two boxes are going to be accelerating together with this acceleration A. And that's what we want to find, right? So we'll just call it A. So that's our first equation, T equals ma. Okay, let me go to the second box. I'll box this in here. So I have, same thing. If I look at the x direction, if we had friction, we'd have to do the y direction as well, but we don't, so we don't have to worry about it. So now I want nx plus fx, right? I want the x components of all these vectors, all these forces, plus w2x plus tx is equal to max. So again, normal force in the x direction is 0. The applied force, it's all of it, right? And it's positive. The weight is 0. And then the tension in this case is all of it, but negative. And that's got to equal m. And the ax is the same a that we're trying to find. So this equation basically says that F minus T is equal to ma. Okay, so what I could do, basically right now, right? Remember, I know F. So I know F, I know the mass. I don't know the tension, I don't know acceleration. So basically right now I have 2 equations and 2 unknowns, right? I have this system of equations. So what I can do is I could substitute, or I could use elimination too, but I'm gonna use substitution. Where I have a t in that second equation, I'm gonna plug in this t, which is equal to ma, right? So I have F minus ma is equal to ma. And then I'm gonna solve this for a. So I'm gonna add ma to both sides. So F equals, this is going to be 2, right? ma. And then finally, if I divide by 2m, here I'll write it like this. I'm going to divide by 2m. Whatever you do one side, have to do the other side, so that cancels. And I get a is equal to F over 2m. And now I can plug in, right? Because I know my force is 500. And I know the m is 20. So the acceleration of that system must be 12.5 meters per second squared. So that's the acceleration. And then to get the tension, I can plug it back into either of these equations, but this one's much easier, right? To get the tension in that rope between the boxes. So I'm going to go back. I know that, so I want to plug into this one, right? I know the mass is 20. And now I know the acceleration of that box, both boxes, is 12.5. So now the tension in that rope between the boxes must be 250 newtons. Okay, so that's probably the best way to do it, to split it up into separate objects, right? The system consists of each box separately. All right. Next question. So you're told a 97 kilogram sprinter wishes to accelerate from rest to a speed of 13 meters per second in a distance of 22 meters. What coefficient of static friction between the sprinter, what is the coefficient of static friction between the sprinter's shoe and track? Assume that the sprinter undergoes a constant acceleration. Okay, so we can deal with constant acceleration equations. And also assume that the shoe is on the verge of slipping. So in other words, the frictional force, the static frictional force that's being applied to the shoe is Fs max, right? Because then it's easier, and we can actually calculate μs. Because if we just said it was Fs, we wouldn't know exactly what the value is, but if we know it's the maximal static frictional force, then we can actually solve for μs. Okay, so probably the first thing I want to do is, given this information, I want to figure out what the acceleration of the sprinter is, right, in the x direction. So if we look at this, okay, let me draw a picture first. So here is the sprinter. There's a normal force acting up. There's a frictional force acting forward. And remember, we're assuming this is Fs max. And what else? And the weight, right? So at the center of mass, the weight of the sprinter is acting down. And that, of course, is equal to mg. I'm going to assume the typical standard coordinate system where x is to the right and y is vertically upward. Okay, so let's look at the y direction first. So I'm going to apply Newton's second law to the y direction. So sum of the forces in the y equals MAY. So in this case, I want the y component of the normal force plus the y component of the weight plus the y component of Fs max. That's got to equal MAY. So the y component of the normal force is going to be all of the normal force, right? It's all in the positive y direction. The y component of the weight will be all the weight but negative. The y component of the max static frictional force is 0, right? That's all in the positive x direction. And we're going to assume that there's no acceleration in the y direction. We're going to assume the sprinter starting, they're just accelerating in the x direction just to make it easier. So that means AY is going to be 0. So that means in this case that the normal force is equal to the weight of the sprinter, right? So N is equal to mg. Okay, and we can calculate that, right? We know the mass of the sprinter is 97, I believe. Yeah, 97. And G, of course, is 9.8. So that's going to be 950.6 newtons. Okay, so that's the normal force. Again, why do I need that? Because ultimately, I'm going to need to figure out the magnitude of Fs max. And remember, that's equal to μs times n. Okay, so I'm going to need that to know the n at some point. All right, what about the x direction? Well, first of all, we need to figure out the acceleration in the x direction. And we're given some information here, right? We know that, so now I'm going to do x direction. So we know that v initial x, since he's starting at rest, is 0. we know that the final speed, right, once after he's done the acceleration is 13. So Vx is 13 meters per second. And we know that the displacement over which he accelerated was 22 meters. Okay. So I want to find AX. I want to figure out what AX is. We're assuming it's constant acceleration, right? So we can use our constant acceleration equations. And notice that this one will work, right? If I use Vx squared, so V final equals V initial squared plus 2AX delta X. And I can solve this for AX, right? If you rearrange this, we've done this a bunch of times. This is going to be Vx squared minus V naught X squared over 2 delta X. And if I plug in 13 squared minus this is 0 over 2 times 22, and that turns out to be 3.84 meters per second squared. Okay, so that's the acceleration. So now, remember, ultimately, we're trying to find mu s, right? The whole goal here is to figure out what that coefficient of static friction is between a sprinter's shoe and the track. So let's see, I know the normal force, right? Now let's go to the x direction. Let's apply Newton's second law to the x direction. So I have sum of the forces in the x direction equals MAX. So now I want the x component of the normal force. I want the x component of the weight. I want the x component of Fs max. And that's got to equal MAX. Well, the x component of normal force is 0, right? It's all acting in the y. The weight is in the negative y, so no x component. But Fs max, the x component is the entire Fs max, right? The entire maximal static frictional force is acting in the positive x direction, and that's equal to MAX. And remember, this is really, Fs max is really mu s times n. Okay, so I could solve this for mu s. I could divide both sides by n now. So mu s is going to be MAX divided by the normal force. So if I work this out, right, this is going to be 97 times 3.84 divided by, and normal force was, what was it, 950? Yeah, 950.6. And that will give me 0.39. And remember, the coefficient of static and kinetic frictions are unitless, right? So that's the answer. So 0.39 is the mu s between the shoe and the ground when the shoe is on the verge of slipping, right? That's how we're able to find mu s. Okay, great. All right, next question. At a given instant in time, a 5-kilogram rock is observed to be falling with an acceleration of 7.0 meters per second squared instead of 9.8. Okay, therefore air resistance cannot be ignored, right? There's some air resistance, there's some other force acting on the object if it's not falling at, it's not accelerating at 9.8. And we want to find the magnitude of the force of air resistance acting upon the rock at this instant. All right, so what I would do is draw a picture first, right? So here's my rock. And I have, certainly the weight is acting. And if that were the only force acting, right, then it would be accelerating at 9.8 downward, right? If you assume no air resistance. But in this case, we're assuming there is air resistance. I'll call that R. And we know that this thing is accelerating not at 9.8 down, but at 7. So I can say AY is negative 7.0 meters second squared, because I'm assuming that Y is positive upward. right? So that means my acceleration is going to be -7. Okay, so now let's apply Newton's second law to the y direction. So sum of the forces in the y equals MAY. So now I want the y component of the air resistance force plus the y component of the weight. That's got to equal MAY. Well, the y component of the air resistance is all of r, and it's in the positive y direction, right? So that's just r. The y component of the weight is all of the weight, but it's negative. So negative mg, and that's got to equal MAY. Okay, I can bring, I guess I can, if I want to solve for r here, right? I'm looking for r. So let me add mg to both sides. So I have r is equal to MAY plus mg. And you could even factor out the m if you want, right? A little bit of math here, and factor out the m, and I have AY plus g. Okay, so in this case, m is what, 5, I think? The mass of this rock? Yeah, 5 kilograms. AY, you got to be careful here, is -7. And then G, because we already took into account the direction of G, is just positive 9.8. And then if you work this out, this turns out to be 14 newtons. So there is an upward force, in this case, of 14 newtons, which makes sense, right? That's why this rock is not accelerating downward at 9.8. It's only accelerating downward at 7.0 meters per second squared. Okay. Next question. So you're told a contestant in a winter sporting event pushes a 45.0 kilogram block of ice across a frozen lake as shown below in the top figure. Calculate the minimum force F you must exert to get the block moving, right? So we have to overcome the static frictional force. What is the magnitude of the acceleration once it starts to move if that force is maintained? Okay. And we're told mu s is 0.1 for ice on ice, and mu k is 0.03 for ice on ice. All right, so first of all, let me draw all the forces acting on that block of ice. All right, so we have the ground here, right? We have, of course, the weight. That's equal to mg. We have the normal force. We have at first, we want to figure out what force is required just to get it to move. So the frictional force is going to be Fs max, right? Just what's on the verge of motion. And then we have this applied force acting at 25 degrees. So it's kind of going like this. Right, and this is 25 degrees. Okay. So this force vector is going to have two components, right? If I draw this out here, this force vector, the applied force, is going to be, first of all, it'll be in the fourth quadrant, like this. This is 25 degrees, and it's going to have an x component, so fx, and then a y component, fy. And we know if we use that triangle there, we know that the fx, x component, will be f times cosine, right, at 25 degrees. And then the y component will be f times sine, but it's negative, right, because it's pointing downward. So it's negative f times sine of 25. Okay, so let me start by applying Newton's second law to the y direction. So sum of the forces in the y is equal to MAY. Why? Because I want to figure out what this normal force is, because again, I'm going to need it because we know that, remember, Fs max is equal to mu s times the normal force. So I'm going to need to figure out that normal force at some point. Okay, so let me add up all the y components. So I have Fy plus Ny plus Wy plus Fs max y. That's got to equal May. So Fy, we just said, was negative F sine of 25 degrees. And all the other ones are going to be right along the axes, right? We're assuming, again, that we have this coordinate system. X is pointing to the right and Y is vertically upward. So Ny is 0. Oh, sorry, Ny is all of n, right? Ny is all of n because it's pointing to positive Y. The weight, Wy, is going to be all of the weight but negative, so mg. And then Fs max y, that's 0, right? Because that's pointing in the negative x direction. And we're assuming that this block of ice is not leaving the surface of the pond. So the acceleration in the y direction is 0. So if we solve this for n here, n is going to be, I need to add those mg and then the other term on both sides. It's going to be mg plus f sine of 25 degrees. Okay, so actually now I could figure out Fs max. Fs max, I'm just going to leave this in terms of variables, is mu s times n. So this is going to be mu s times mg plus f sine of 25. So that's going to equal, I'll distribute to mu s mg plus mu s f sine of 25 degrees. Okay, let's go now to the x direction. Can't do much more with the y direction. So now in the x direction, I have sum of the forces in the x direction equals max. So now I want the x component of the applied force plus the x component of the normal force plus the x component of the weight plus the x component of Fs max. That's got to equal max. So the x component of the applied force, remember up here, we already found it. It's F times cosine of 25. The x component of normal force, none of that normal force is in the x direction. Same thing with the weight. But the x component of the applied force is the entire Fs max, but it's negative, right? So this is negative Fs max. And that's got to equal max. But because this is not moving yet, right? We're on the verge of motion. We're trying to overcome that static frictional force. So ax is actually just 0 right now. Okay, and if I plug in Fs max, I have this. So F cosine of 25 minus, and remember Fs max is going to be mu s mg, and then I have minus, you have to distribute the minus in both of those, mu s f sine of 25, that's got to equal 0. Okay, I'm subtracting this whole thing. So I have minus this, minus this. Now, what are we trying to find here? Remember, we're trying to find the applied force, right? What is the magnitude of F? We're trying to find the F here. So I need to solve this for F. Okay, so if I solve this algebraically for F, let's see, I'm gonna have F times cosine of 25 minus mu s F sine of 25. And I'll bring the other term to the right-hand side, so it becomes mu s mg. And then if I factor out an F, that's mu s mg. And then finally, I can divide both sides by cosine of 25 minus mu s sine of 25. Right, that'll cancel, but whatever I do to one side, I better do to the other side. So a little bit of algebra here. This is mu s sine of 25. And then I can plug in. I need a little more room here, so I'm going to do it over here. So I have f is equal to mu s mg over cosine of 25 degrees minus mu s sine of 25. Okay, so this is going to be mu s was 0.1, right? M was 45. G, of course, is 9.8. Then I have cosine of 25 minus, and then it's 0.1 times sine of 25. Plug that into your calculator. Be careful with order operations, and you're going to find that force is 51.0 newtons. So that's the force that was applied, right, to this block of ice here. So if it's just on the verge of motion, given all this information, then that's the force that has to be applied. So it's just on the verge of motion, 51.0 newtons. Okay, so that's part A, right? We found F. Part B is, what is the magnitude? So now we want to find the acceleration in the x direction, given that that force is applied, and now the force it's resisting is a kinetic frictional force, right? Which is going to be smaller than that max static frictional force. So now it will accelerate to the right, and we want to figure out what that acceleration is. So we're basically going to do this over again, but now we know that applied force, right? And we know instead of Fs max to the left, we have Fk acting to the left. So let's do this again. Here, I'll draw the picture again. So I have the weight. I have normal force. I have now it's a kinetic frictional force, right? That's resisting it. I have the applied force, which I know now. The value is 51. Acting down like this at the same angle, 25 degrees. Yeah, so I know this is 51.0 newtons. And I know now that mu k is 0.03. And I want to find AX. That's what I'm looking for. What's the acceleration of this block now? Okay. So again, let me write out Newton's second law for the y direction first. So sum of the forces in the y equals MAY. So I want the y component of the applied force plus the y component of the normal force plus the y component of the weight plus the y component of Fk. That's equal to MAY. But the y component of the applied force is again going to be, so that'll be the same as for negative F. We know what F is now though, right? Negative F times sine of 25. I'll leave it like that for now. The normal force is all of N. The weight is minus mg. And then the y component of the kinetic frictional force is 0. And it's still not moving in the y direction, right? So the acceleration is 0. So basically, this just tells us, by rearranges, that N here is going to be mg plus F sine of 25 degrees. Okay, and then again, since we know that Fk is equal to mu k times N, then I can plug that in here. So mu k times, and then N is mg plus F sine of 25. So if I distribute this mu k, then Fk here is going to be mu k mg plus mu k F sine 25. Okay. So that, again, I need to do the y direction because I needed to find normal force, and I needed a normal force I could plug in here to figure out the magnitude of that kinetic frictional force. Now let's go to the x direction. So now I have sum of the forces in the x direction equals max, right? We're trying to figure out what the ax is. So now I have the x component of the applied force, the x component of the normal force, the x component of the weight, the x component of the kinetic frictional force, that's equal to max. So the x component of the applied force was F cosine of 25. The x component of the normal force was 0, of the weight is 0. And then of the frictional force, it's first of all, it's all of Fk, but it's negative. And that's got to equal max. And we just found Fk, right? So if I substitute this value in, this expression in for Fk here, I'm going to have minus, and then again, you got to be careful, right? It's minus, and then it's parentheses the entire thing. Here, I'll write it out for you. Mu k mg plus mu k f sine of 25 is equal to max. And now if I distribute in that minus 1, it makes both those terms negative. So it's minus mu k mg minus mu k f sine of 25 equals max. Okay. And then because I want to find ax, I can simply divide both sides by m, right? If you want, you could factor out an f here. Here, I'll write it one more time. I'm going to put this on the left-hand side because I want ax on the left-hand side ultimately. So this is f cosine. I'm going to write the other term containing f next to it. You don't have to do this part, but just a little neater algebraically. And since the f is common to both of the first two terms, I'm going to pull it out, and I'm left with cosine of 25 degrees minus mu k sine of 25 degrees, and then minus mu k mg. And now I'm going to divide both sides by m. Right, so m's cancel. So I have ax is equal to f times cosine of 25. Oops. Minus mu k sine of 25 minus mu k mg, all divided by m. Okay, and then you can plug in, right? So if we plug in, f, remember we found was 51. Cosine of 25, whatever that is, you can do that on your calculator. Mu k was, what was it, 0.03, right? So 0.03 times sine of 25 minus 0.03 times m, which was 45, times g, 9.8, all divided by 45. And if you, again, work that out, just be careful. You're going to get that the acceleration of that block of ice is 0.719 meters per second squared. Right, so that would be the answer. So if you kept with that same force, remember it required 51 newtons to get it started to overcome the static friction, but then you kept applying the 51 newtons, then the thing is going to accelerate at 0.719 because now the kinetic friction is smaller acting to resist it, right? So it's going to accelerate to the right with that acceleration. Okay, the next question is basically the same thing, but instead of pulling, instead of pushing on the ice with that force, you're pulling with a force. In this case, we're calling it F prime. So we're going to repeat the same thing over again, but now instead of pushing, So instead of pushing down here at 25 degrees, we're pulling up at 25 degrees. And that's going to change things, right? Because it's going to affect the normal force. It's going to affect what that max static frictional force is. It's going to change a couple of things. All right, so same situation. Let me draw this out. So what are the forces acting? Well, I have the weight. I have the normal force. I have this applied force now, which is up, which we call F prime. And this is 25 degrees. And then at the beginning, I'm trying to figure out just that force to get it moving. So this is Fs max. That's resisting it to the left. Okay. Because I'm pulling up instead of pushing down, that's going to change the entire normal force, right? That's why we do need to do this again. I can find, let's start by finding the components of F prime. So if I project this onto the x-axis, this is F prime x, project it onto the y-axis. This is F prime y, right? And this angle is 25 degrees. So it turns out that F prime x is going to be F prime times cosine, right, of 25. And it's positive, it's pointing to the right. And then F prime y is F prime times sine of 25 degrees. And it's positive, right? Because in this case, it's pointing up. Whereas in the other case, when you're pushing, it was negative, right? It was down, but in this case, it's up. Okay, so let me start by applying Newton's second law to the y direction. So I have sum of the forces in the y equals MAY. So I want the y component of F prime plus the y component of the normal force plus the y component of the weight plus the y component of Fs max. That's equal to MAY. Well, what is the y component of the applied force? So again, we're assuming, right, the standard coordinate system where x is to the right and y is vertically upward. Well, that's what we just found, right? The y component of F prime is this. It's F prime times sine of 25. So this is going to be F prime sine of 25 degrees. The normal force is all of the normal force, so it's N. The weight is all the weight but negative, so minus mg. And then the y component of the static frictional force is 0, right? And it's not moving in the y direction, so the acceleration in the y is 0. So if you rearrange this, if I solve for n here is going to be mg, right? I have to add it. So this is where it changes. Mg minus F prime sine of 25. Remember in the other example where you're pushing, n was mg plus F sine of 25. In this case, it's mg minus F prime sine 25. And then why am I even getting n? Because to find Fs max, that's going to be mu s times n. So if I multiply this, right, this is going to be mu s mg minus mu s F prime sine of 25. Okay. Remember, our whole goal here is to figure out mu s, right? Our goal is to figure out mu s, just like we did with the other problem. Okay, now let me go to the x direction. So sum of the forces in the x direction equals max. So now I have the x component of F prime plus the x component of the normal force plus the x component of the weight plus the x component of Fs max. That's got to equal max. So x component of F prime was just F prime times cosine, right, of 25. There's no x component of the normal force, no x component of the weight. And then the x component of Fs max was negative that entire magnitude of Fs max. So just negative Fs max, right? And that's got to equal max. But ax is 0 in this case, right? Because remember, this is just on the when it's on the verge of moving. So it's not accelerating yet, so that's 0. Okay, so again, if I substitute Fs max in here, it's going to be minus mu s mg. And remember this, so I have to distribute this -1 in, right? So this term becomes minus, this term becomes positive, plus mu s f prime sine of 25, and that's equal to 0. And then I want to solve this for f prime. So I'm gonna put the f prime terms together. I'll bring the mu s mg to the other side. And then I can factor out an f prime. And then finally, I can divide both sides by cosine of 25 plus mu s sine of 25. So this will cancel, right? And then here, I need to divide it on this side. Okay, and then we can solve for f prime, right? If I plug in, so this is going to be 0.1 times 45 times g, which is 9.8, divided by cosine of 25, whatever that is, your calculator will figure it out. Remember, mu s was 0.1, and then sine of 25. Oh, I think I mistakenly said we were solving for mu s. We're not solving for mu s. We're solving for f, what this force must be, right? So that it's on the verge of motion. We know mu s is 0.1. All right, so f prime here, if you work this out, is going to be 46.5 newtons. So actually, it's a little bit less, right? Because last time it was 51. So it's a little bit less if you're pulling on it instead of pushing on it. Because now the normal force is less. So it kind of makes sense that it would be a little bit less. All right, so that's our answer for f prime. And then the second part, again, we're duplicating what we did earlier. Now that we apply this force, assume now it's moving, right? So now there's a kinetic frictional force. Now we want to figure out the acceleration, right? If the same force is applied now to that box. So I'm going to draw this again one last time. So here is my box. We have all the forces acting, right? The weight, the normal force, the applied force, which we know now, right? F prime at 25 degrees. And now the force that's resisting now is going to be a kinetic frictional force, right? Because you're assuming it's moving. And what we're trying to find, this thing is now going to be accelerating to the right. We're trying to find the acceleration AX. Okay, so again, we know F prime, we know that magnitude now is 46.5. We know mu K, that was 0.03. And we're trying to figure out that acceleration. Okay, so I have to walk through this again, right? Let's look at the y direction first. Again, using our standard coordinate system. So I have the sum of the forces in the y direction is equal to MAY. So I want the y component of F prime plus the y component of the normal force plus the y component of the weight plus the y component of Fk. That's equal to MAY. The y component of F prime is going to be F prime, which we know now, right? Times sine of 25. I'll just leave it as F prime. Y component of normal forces is all of N. Y component of the weight is minus mg. Y component of the kinetic frictional force is 0. And then it's not moving in the Y direction, so acceleration is 0, so that's 0. So again, if you're going to get N here, is going to be mg minus f prime sine of 25. And why do we need to know that? Because now fk is equal to mu k times n. So this is going to be mu k mg minus mu k f prime sine of 25. Okay, so I needed to figure out the normal force. So I had to look at Newton's second law in the Y direction so I could figure out the normal force, which allowed me ultimately to plug in here to figure out fk, the magnitude of fk. All right, so now that I have that, let me go to the x direction. So I have sum of the forces in the x direction equals max. So now I want the x component of f prime plus the x component of the normal force plus the x component of the weight plus the x component of fk. That's got to equal max. And our goal now is to figure out the ax. So x component of f prime is f prime cosine of 25. There's no x component of normal force, no x component of the weight. And an x component of fk is minus the entire fk. Okay, so now I'm going to substitute in fk. So again, minus, and I have to distribute into an entire fk, so it's minus mu k mg, and then it'll be plus mu k f prime sine of 25 is equal to max. Just like before, I'm going to factor out, so a little bit of algebra here. I'm going to write this max on the left-hand side. On the right-hand side, I'm going to factor out an f prime. So I'm left with cosine of 25 degrees plus mu k sine of 25. And I also have this minus mu k mg. And then I can divide both sides by m. Right, and that gives me what I want, which is ax. So ax is going to be f prime cosine of 25 plus mu k sine of 25 minus mu k mg all over m. Okay, so let's plug in. So I know f prime was 46.5. I have a cosine of 25, whatever that is as a decimal, but you can work it out in your calculator, plus 0.03 sine of 25 minus 0.03 times 45 times 9.8, all divided by m, which was what, 45? So again, carefully plug that in. If you work this out, ax is going to be around 0.656 meters per second squared, right? So if you continue pulling with that same force that you needed to get it started, that would be the acceleration in the x direction, okay? So those two problems were a little bit more work, a little bit more algebra, but really the same process holds, right? We had to apply Newton's second law to the y direction, basically to calculate the normal force, so then we could figure out the magnitude of the frictional force. And then we had to apply Newton's second law to the x direction. Okay, so same process holds. All right, hopefully that was helpful. Thanks.